let's return to these formulas that I gave you earlier, that the probability of A intersect B is the probability of A times the probability of A given B. Also, it can be written the other way around, probability A times probability of B given A. So let's take a look at how we might use that. So I find these examples in this section to be easier to follow if we draw these tree diagrams. So suppose we send 30% of our products to company A and 70% of our products to company B. So if you look down here, you can see that I've got a branch coming off to company A. 30% is 0.3, so 30%. So there's a 30% probability that we'll send a product to company A. And then at B we get 0.7, so there's a 70% chance we'll send it here, so the probability there would be 0.7. Now, we also know that company A reports that 5% of their products are defective, and company B reports that 4% of our products are defective. So in other words, when we send that to company A, when company A tests them, they find that 5% are defective. So that's where we get the 0.05. And if 5% are defective, then that means 0.95 or 95% are not defective. So that's the D prime, just means not defective. Now, for company B finds 4% defective, so therefore they would find 96% not defective. So now, from this, I can answer some interesting questions. A says, find the probability that a product is sent to company A and it is defective. Okay, this and here tells me that I'm looking at an intersection. So what I'm wanting to find is the probability of A intersect D. A intersect D. And then this one, company A, and is not defective, so I'm looking for the probability of A intersect D prime. And then likewise here, I'm looking for the probability of B intersect D and B intersect D prime. Okay, so let me just give you some information that we can determine from this table. I've already shown you how I filled out the tree diagram, but this 5% right here, this is actually a conditional probability, because you don't get this 5% unless it came from company A. So technically this is the probability that the product is defective given that it went to company, actually I guess I should say came from company A, but anyway, given it came from company A. So this would be the probability of defective given A. So this 0.05 here, it's the probability of defective, but it's the probability of defective given that we sent it to company A is what we're saying. So probability of defective given company A. Now the 0.95 is the probability of not defective given company A, and then likewise this 0.04 is the probability of defective given company B, and D prime is the probability of not defective given company B. Okay, so if we want the probability that it went to company A and it's defective, we can just take the probability that it went to company A times the probability that it's defective given A. Well, if you actually go up here and look at this, all we're doing to get this probability of A and D is we're just multiplying these two branches from A to D. So all we really have to do to find the probability of A intersect D, obviously we can use this formula, but all we really need to do to find the probability of A intersect D is just multiply the branch for A, 0.3, times the following branch for D, 0.05. So 0.3 times 0.05 is 0.015. Now, if we want the probability of A intersect D prime, then that would be the probability of A times the probability of D prime given A. Well, again, that's 0.3 times 0.95. So the probability A intersect D prime is 0.3 times 0.95. And then likewise, if we want the probability of B intersect D, we just take the 0.7 times 0.04, like I did here. And then if we want the probability of B intersect not D, we take the 0.7 times 0.96. Okay, so now you can see here that even though I used formulas here, it's actually just simply multiplying the appropriate branches together to get these probabilities of the intersections. Okay, so long story short, if I want the probability of A and D occurring, then I just multiply these two branches together. And similarly for the others. Alright, now what could we ask next? Well, next we could say, what is the probability that an item is defective? That should say AN, not A and D. The probability that an item is defective. Okay, now I just want the probability of defective. Now, here's the key. There's two ways the item can be defective. The item can be defective if, sorry about that, let me get back to where I was. So the item can be defective if it went to A and it was defective, or if it went to B and it was defective. So in other words, I need to calculate the probability of A and defective, in other words, A intersect D, and then calculate the probability of B and defective, B intersect D, and then just simply add those two together, and that'll give me the probability of defective. So if you take a look down here, the probability of defective, I just multiply the paths to defective together. So one way to get to defective is A intersect D, so that would be the 0.3 times the 0.05, or 0.015. And the other path to defective was B intersect D, and that was the, what was B intersect D? The 0.7 times 0.04, and that's how I got the 0.028. And then I just add those two together, 0.043, and then that gives me the probability that an item is defective. Now that's not a conditional probability, that's simply the probability that an item is defective. Now, what if I wanted to know the probability that an item is not defective? Well, common sense tells me I could just subtract this from 1 since it's the complement, but let's do it the way I did this first one. So the probability of not defective must include both ways it could not be defective. So it could go to A and not defective, so that's 0.3 times 0.95, or 0.285. Or it could go to B and not defective, which is 0.7 times 0.96, which is 0.672. And so add the 0.285 to the 0.672, and guess what you get? You get 0.957, which of course is the same thing we would have got if we'd have just subtracted 0.043 from 1. So anyway, that's how you can find the probability of a part being defective. So let me kind of explain what that means. What we're saying is, if we randomly selected an item and we wanted to know the probability that it's defective, we could calculate it by multiplying these two together and then multiplying these two together and then adding them up, and that would be the probability that it's defective. Let's continue this with another similar example. Let's say a box has 7 red balls and 3 white balls, and a second box has 6 red balls and 4 white balls. A pair of dice are tossed. If the sum of the dice are less than 5, a ball is selected from the first box. Otherwise, the ball is selected from the second box. Find the probability of getting a red ball. Well, the first thing let's do, let's draw the diagram. This is box 1, And so if you actually calculate how many numbers are less than 5, there are actually 6 ways that you can get a number less than 5 if you toss a pair of dice. So these are the 6 ways to get a number less than 5. So the probability of getting a number less than 5 is 6 out of 36, which reduces to 1/6. So in other words, the probability you select from box 1 is 1/6. Well, if the probability selected from box 1 is 1/6, then of course the probability selected from box 2 must be the complement, 5/6. Okay, now let's say we select from box 1. If we select from box 1, what's the probability we get a red ball? Well, there's 7 red balls out of 10, so 7/10, and the probability of white ball would be 3 out of 10. Now if we select from box 2, there's actually 6 red balls out of 10, so 6 out of 10 reduces to 3/5, and there's 4 white balls out of 10, and 4 over 10 reduces to 2/5. So that's your tree. Now, the answer to our question, remember, said what's the probability of red? Now notice there's 2 ways to get a red ball. You can select from box 1 and get a red ball, or you can select from box 2 and get a red ball. So how do we find the probability of a red ball? We multiply the probability from box 1 times the probability of red, so that would give me, where's it at? I'm just going to go ahead and show you. That would give me the 1/6 times the 7/10, and then we multiply the probability of box 2 and red, so that would be 5/6 times 3/5. And then when we multiply these and we have to add the 2 results together, we actually get 37 out of 60, which is 0.617. Now if you think about that, you know if you draw a ball, you're going to get either a red ball or a white ball, so we could easily get the probability of a white ball by just subtracting this from 1 and get 0.383. But let me just show you it works if you use the formula too. Let's find the probability of a white ball. Well, white ball would be 1/6 times 3/10, because box 1 and white ball, or box 2 and white ball, which would be 5/6 times 2/5. So we would say 1/6 times 3/10, and then 5/6 times 2/5, and then we would add these 2 numbers together, and it turns out if you add these together, you actually get a decimal that's approximately 0.383. Okay, so the conclusion here is that we can easily calculate the probability of a later event, such as a red ball, given the probability of an earlier event, such as box 1, from the table. So that would just be the probability of red given box 1 is just the top branch, which is 7/10. And we can also calculate the unconditional probability of red or W as I did above. Now, the next video I'm going to show you something that's interesting. Rather than finding the probability, let me go back up here. Rather than finding the probability of a red ball, given that it came from box 1, I'm going to show you that I can actually calculate the probability that it came from box 1, given that I knew the ball is red. Well, that's actually finding the probability of an earlier event, given the probability of a later event. And to do that, we're going to need Bayes' formula, which I'll introduce in the next video.